We have two more ideas that we want to take a look at before we dive fully into this process of identifying all zeros for a polynomial function. The first is a theorem that tells us that every complex polynomial has exactly n complex zeros. Some of which may repeat. That tells us that if we identify the degree of our polynomial, that's going to tell us exactly how many zeros we should be able to find for that function. A complex number R is called a complex zero of a function f if our function evaluated at that number gives us a result of 0. So that idea is not any different than the idea we've established before, what it means for a number to be a 0. We also want to keep in mind the idea that the real numbers are a subset of the complex numbers. So when we talk about the idea of complex zeros, we're including the idea of real zeros. If a complex number, R1, is something of the form a plus bi, meaning it has both a real and an imaginary component, then we could also consider a number, say R2, where a plus bi is actually equal to a plus 0i, meaning this number has a real component, but the imaginary component is equal to 0. So that complex number would just be equal to a, making it a real number, but just a special case of our complex numbers. Again, we just want to keep in mind that idea. If we're talking about complex zeros, we include real zeros as a subset or included as part of our solution. The last idea that we're going to need is the idea of the conjugate pairs theorem, which tells us that for a polynomial function f, whose coefficients are real numbers, if r equals a plus bi is a complex zero of that function f, then so is its complex conjugate, which is denoted as r bar, so r with a horizontal line over it, a minus bi. So almost identically the same number, but we swapped out that plus for a minus. We can use this to complete the next three examples. If in example 11, we have a polynomial function of degree 3, whose coefficients are real numbers and has zeros of -9 and 3 minus I, we can find the remaining zeros for that function. In this case, our function is degree 3, so there are exactly n equals 3 zeros we should be able to identify. 2 of them are provided for us, which are -9 and 3 minus I. So the remaining zero, that third one in our list that we should be looking for, would be the complex conjugate of that complex number, so 3 plus I, where again all that's changed is the sign in between the real and imaginary part of that complex number. In example 12, a given function g of x has a degree 4. That means there should be exactly n equals 4 zeros that we're trying to identify. We're given I and -5 plus I as 2 of the zeros. That means there are 2 missing that we need to identify. Keep in mind that even though we don't write it, the number I is the same thing as 0 plus I, where 0 is that value a, the real component of that imaginary number. This means we can identify 2 additional zeros by constructing the complex conjugates, which would be 0 minus I and -5 minus I. And then of course 0 minus I we could go ahead and just simplify down to simply minus I. In example 13, we have a polynomial of degree 6, meaning there should be exactly 6 zeros that we would find. If we're given a few of those already, 7, 8 plus I minus 2 minus I and 2. That means we have 2 that are missing. But again, we can find those by constructing those complex conjugates to round out that full list of zeros for this function. This is going to be another tool then to help us check and verify that we're on the right track with our solutions. For any given polynomial, we can identify its degree, and from there we know exactly how many zeros we should find. In this case, if we didn't come up with 6, or if we came up with more than 6, we would have the wrong number of zeros. And anytime a complex number is a 0 for that function, we should also have its complex conjugate as an additional 0 for that function.